Diagnostics. Diagnostics are a set of tools to assess how well the model is fitting. The Rsquared is one such diagnostic. It is the first one that we learn about. Rsquared explains what percentage of the variation in Y the model is able to explain. And Rsquared is also called the coefficient of determination. So just to elaborate on that second point, Y varies, right? Y is not constant, it varies. And in regression, we're trying to understand how the X variables relate to the variability in Y. And Rsquared is one measure of what the model is doing. And it specifically tells you what percentage of the variability of the variation in Y the model can explain. So the total sums of squares can be partitioned into two elements, the model sums of squares, here's the sums of squares regression, and the residual sums of squares, or the sums of squares error. The total sums of squares is just the observations, yi, minus the grand mean, or the average of all the observations. So here's the total sums of squares. The next simplest term is maybe the sums of squares of residual, or sums of squares errors. Both terms are used. And here we have the observation, yi, minus the predicted value of that observation. So these together are the residual, and then we square the residuals, we have the sums of squares here. And then what is left over is what the regression model is able to explain, the sums of squares the regression model can explain. So here we had the difference of yi minus y bar squared. Here we had the error squared. And here we have the predicted values minus y bar squared. That this equality holds is not completely obvious. One does have to show it, but we're not doing that here. Similar partitions will show up from time to time in this course. Let's look a little bit more at what this means. Okay. So actually, before we look at what it means, let's first define what Rsquared is. Rsquared is the sums of squares regression divided by the total sums of squares. And because of that equation on the last slide, the sums of squares regression is the same as the total sums of squares minus the sums of squares error. And then isolating that, we get 1 minus sums of squares error divided by sums of square total. So from that, we can see sums of squares are positive, right? So we divide something here, the two positive numbers, we get another positive number. So we see that Rsquared is bounded above by 1. So Rsquared is smaller equals 1. And, equal can happen if SSE is 0, if it's a perfect regression. On the other hand, it's also bounded by 0 because sums of squares regression, well, a terrible model, will not explain any sums of squares. And so we would have 0 in a worst case scenario. So it's between 0 and 1. Rsquared equals 0 means that the regression line is horizontal. It doesn't explain any variation. R squared equals 1 means that the data perfectly fit on a regression line. It is the most widely used single number diagnostic. And yeah, as we've mentioned, it explains what percentage of variation in Y is explained by the regression model. So I keep talking about variation explained, but on the slides, we always had sums of squares, and you may wonder why I use the word variation when in fact the formula is sums of squares. And that's because the sums of squares are easily converted to variation simply by just dividing by a constant. So if we have the sums of squares total on the left-hand side here and divide that by n minus p plus 1, p the number of x variables, plus 1 for the beta 0, we have here the estimated variance. And so if we divide it on the left-hand side, we have to divide it on the right-hand side. So here we have the portion of the variance explained by the model. It's just divided by a constant. And here the portion of the variation not explained by the model, the error. So whether we talk about sums of squares or variation doesn't matter because the denominator here is constant. All right, now let's look at some graphical explanation to explore this a little bit further. R squared measures how much of the variation in Y is explained by the model. Yeah, I have two models actually here. One that you will recognize, there's a regression line, that's the linear model with one X variable. And then in addition, I have the two lines corresponding to one standard error above and below. So this is this line and that line. And then I have here another model, but you might not recognize it as such because the model says that Y is always predicted by the average, by Y bar. Now, and I have variation around this, of course. Because I always predicted by the average Y bar, I don't really need the x-axis, which is this, why this is just on one point here, and this has different values for a range of different x values, right? And you see the variability of this very simple model is much larger as expressed by the one standard deviation, for example, this pink bar. The pink bar is much larger than the one standard deviation over here, which means that this model, so including the x variable, seems to reduce the leftover variation not explained by the model by quite a bit. And so I also want to point out that the variation here is the same regardless of at what x value I am, but that's by assumption, right? So in linear regression, we assume that the variability is constant regardless of x. It's just sigma squared, and it's not sigma squared as a function of x. So the fact that this variability is the same here everywhere as estimated by the model is by design, by assumption. Okay. I think I've said a lot of this already now. By assumption, the variation is constant. The reduction in variation is due to the model. And the variation around the mean of Y is very large. And the mean of Y might be considered a very simple model. And here is that intercept-only very simple model. It's Y equals beta 0 plus epsilon. Whereas here we have the full model with many x variables. Of course, in the graph on the previous page, only one x variable. So the R squared then can also be motivated from the estimates of sigma squared from the intercept only model relative to the estimates from the full model. Here is another explanation. And I'm gonna add, if you don't like this explanation that is coming, that I'm about to say, you can ignore it. You may have already had enough explanation. If you understand it in the other way, it's fine. So I again have the regression line here, and then I have the simple line where regardless of what x is, we are always predicting the average of y, right? So y equals beta naught. And here I have y equals beta naught plus beta 1x. So this example only has 4 points, 1, 2, 3, 4, and the same over there. And what we're looking at is the sums of squares. And because it is the sums of squares, we can visualize this by looking at the area here. So the residual I obtain simply by dropping down the distance between the regression line and the observation. And if I square this, then I get this area. Likewise, for this point, I have a larger residual and I have a much larger area because it's squared. And same down here, right? I always go, I have to go up to the regression line and get the squares. Now, the point here is that the sums of squares is the sum of these 4 red squares. That's the total sums of squares. And the sums of squares error is the total sums of squares of these 4 smaller squares. So what the model has done, it has reduced the variation from something quite large to something very small. All right, so here is a question for you. We can